Okay, thank you so much for the introduction. First of all, I'd like to thank you all for attending this webinar about water flooding, monitoring, and surveillance. Um, uh, do you hear me like very well, or I need to do something? Please, if you don't hear very well, raise your hands or write in the comment box. Water flooding, monitoring, and surveillance, which is like the very important stage in the secondary recovery in the life of oil fields, to maintain the reservoir pressure and also to maintain the productivity of the reservoirs. So this webinar provides tools and procedures that will include sort of prediction techniques to support in surveillance of ongoing activities and also aids to in the process of altering an initial water flooding design for mature fields, if you have to. Before I start talking about water flooding, I will prefer to introduce myself. My name is Abdurrahman Grada, a reservoir engineer. I've been working for a Kakosol operation company for 4 years now. Actually, during the 4 years of experience, I have really enjoyed interpreting and analyzing data like RFT, PVT, and PLT, and many other things. And this is exactly what led me to understand the reservoir features and help me to make the right decisions in many cases. I've been involved in a variety of projects like water flooding projects, well stimulation projects. Actually, it was in sandstone, acidizing treatment, and we managed to create a roadmap to help my company to identify all the problems that we have in our wells and accompanied with the proper solutions. Another project is a field development plan, which was made like from scratch under supervision of Schlumberger. And it's been like a great experience since we've been through, conventional reservoir engineering and of course, dynamic simulation modeling. I have a master's degree from Polytechnic University of Madrid. And before that, I have a bachelor degree from Tripoli University in 2015. So let us start our presentation. Here we have the table of content. We will start with the concept of water flooding and why we need to invest our money to do water flooding. And after that, we will quickly pass through the main stages of the water flooding from the end of primary depletion until the end of water flooding project. Then we will try to analyze the performance of water flooding on the field level. And then we will zoom into the pattern level, based on different criteria, as we will see later on. Okay, and finally, we will go even deeper to analyze the well level, and we will see, some useful diagnostic plots. So as you may notice that in the first part of the webinar, we will be like more theoretical things, and then we'll move on to more practical approaches that we will have some real data, and of course it will be like full of surprises. In our journey of water flooding, monitoring, and surveillance, we will pass through different topics, and you should cover the main related topics that is related to water flooding. We will have some production plots like production and injection history, where we will analyze the history or the production history of like a field, and then we will analyze the pressure response to the water flooding performance. And then we will know about the pattern analysis, how many patterns do we have, and like what are the factors that controlling these patterns. Then we will have the VRR, or voidage replacement ratio. So we will know what is VRR and why it's important to know. And have you ever heard of the conformance plot and how can be in a use of water flooding projects? Then we will take some time to talk about the conformance plot. And then we have the heterogeneity index. This is a very important way to analyze the flooding in a well level. And then we will have some diagnostic plots that, like Chang graph and hole plots that identifies if there is, coning, channeling, what's the status of the injector. I mean, is the injector in a good health or not? So we will like see all these things in this presentation. The methods and the process that will be presented in this webinar emphasize practical uses and their ties to the field data and the geology. So always keep in your mind that the implementation of a proper injection, production, and the pressure surveillance. I mean, these are the triangle elements. Scheme is the key factor in evaluation of water flooding performance, and of course can actively help identify the recovery improvement opportunities. And also creating a direct approach to the reservoir management and analysis of water flooding project to be used when preparing further simulation studies to quantify the factors somehow limiting the recovery, and of course to determine if the oil recovery can be improved or not. And actually this is what the management would like always to hear from a reservoir engineering. I mean, there are rooms for improvement, the recovery, and this is the main target of the reservoir engineer. Here we go. As you may know, that oil production is separated into three main phases. We have primary, secondary, and tertiary, which is known as the enhanced oil recovery. For the primary, oil recovery is limited to hydrocarbons that naturally rise to the surface, and sometimes we use some artificial lift like ESP or gas lift. So let's start with the first blue curve, that is primary, when we are depending on the reservoir pressure to produce the oil. But you should agree with me that with the time you keep producing, the pressure of the reservoir will be depleted. So we need to boost it up. We need to enhance it by doing an artificial, we need to add a source of energy, what we call it a secondary recovery. So the secondary recovery is an important stage in the life of the oil fields, when the reservoir pressure is reduced to a point where it's no longer effective with more hydrocarbons to the producing wells. So we need to inject water or gas to increase the pressure in that reservoirs. So we move on to the red area. In the red area under the secondary recovery, you have two titles, one called the gas injection and the other called the water injection. So the gas and water injection, both of them come under the title of secondary recovery. And today I talk about only water injection, and maybe when I get the chance to talk about the gas injection in other sessions, of course I will do. Then after the secondary recovery, the question will be, after the flooding has been done, what should I do to increase the recovery? So we come to the green, to the green area, and we say that we'll do something called tertiary recovery. That could be something else, like rather than water. It could be water with some chemicals inside. It could be polymer, it could be surfactant, it could be water mixed with other additives to make more recoverable oil. So these are the most common approach of the enhanced oil recovery. So in our case, that we start doing water flooding after the end of primary recovery. In some situations, and like some situations that have already experienced it, that we start secondary recovery from the first days or from the first years. It depends on the drive mechanism, and it depends on the natural energy, if it does exist. So here we have a very basic concept, and everybody should know it, which is what's the difference between water flooding and water injection. Until this slide, I've been saying water injection all the time, assuming they are the same, but from this slide on, there will be a difference between water flooding and water injection. Okay. Once we inject water into the aquifer, that's called a water injection, as it is in the left side of the picture that I have. Okay. And as you may notice that the water injection well is much deeper than the water flooding well because we go deep inside into the water aquifer to build up the pressure. So the main target is building up the pressure. However, in the water flooding, we inject water into the oil zone in the blue area, in the blue zone as you have it here. Okay, as you can see in this slide, to increase the sweeping efficiency. I mean, there is something in addition to the pressure maintenance is the sweeping efficiency. So once we do water flooding, we are actually talking about sweeping efficiency. So if someone asks you which one is good for building the pressure, you would say the injection is good to restore the pressure and also to build up the reservoir pressure. And if someone asks you which one is good for sweeping the oil, the flooding is good for sweeping efficiency and is good for increasing the total recovery. So the injection and flooding are different applications for oil production, which is part of, they might consider to be as an EOR. Okay, so let's go deep about water flooding. Water flooding is a process of injecting water into the reservoir to recover oil that left in the pore space at the end of primary recovery, as we have been said already. And water is injected into the oil zone that physically displacing the oil residing in the pore space and moving it towards the producers. So usually the production and the injection wells are arranged in a variant schemes or patterns to achieve, efficient oil displacement by water. And these patterns are designed to accommodate, variations in the reservoir properties and the fluid distributions. And of course, you might take in considerations the project life considerations and the project economics as well. So before you start thinking about water flooding, you have to know at least the basic knowledge about the geological features, about the rock properties, and what's the lateral communications and what's the aerial and vertical communications along the structure. So that's why, water flooding is a really critical thing. Why? Because we are actually injecting in our important zone, which is an oil zone. And here we have what are the main factors that we should consider while we are doing water flooding. The first thing is the reservoir geometry. You need to know the reservoir geometry. You need to know the shape of the reservoir. Like, is it radial, spherical? Is it like fold or anticline? Is it a salt dome? So that's an important thing. You need to know the geometric reservoir. And then you need to know the oil properties. What is the API and what is the water content? What's the gas oil ratio and what's the viscosity of the oil? And also you need to know what's the formation volume factor. So some of you might ask, why do we need to know, for example, an API? I would say that in some situations where we have a very heavy oil, like with low API, so it's not actually recommended to do water flooding. I mean, it's not recommended to do a pure water flooding. We might need an extra thing that we need to do while we are injecting water. For example, by heating that water before injecting. Sometimes we need to add surfactant to make the displacement process much, efficient. So that's why you need to understand the PVT or the fluid properties before thinking about the water flooding. And then we have you should know the reservoir lithology. Why do you need to know the reservoir lithology? Actually, we should be aware of if there's any clay content and the mineralogy of the reservoir section. Okay, for example, if you have like too much clay content and the water attacks that shale content, the shale will swell up and then closes or at least reduces the permeability. So the injected water cannot move any further. Okay, so this is something that you have to be aware of it before start injecting. So if you have a clay content, try to think of adding a new material that prevents that swelling up, or try to go up with a completely different method rather than water injection. Or also, if you have any natural fractures that will happen, what do you think will happen if you have natural fractures? The injected water, it will escape everywhere, and that's what we call the water fingering. I mean, which means that water takes the wrong path due to the heterogeneity. So I will not get a good sweeping, and the water will run very fast, leaving oil behind. As the photo that you have here, you can see the water goes everywhere and follows the easier path. Whenever it has high permeability, it follows that path, and the efficiency of sweeping is like miserable, because the water will be produced very fast, and we will leave a lot of oil behind, and this is the worst scenario. Okay. So what we might do in these situations, we might actually think about, adding polymer. We might inject polymer with the water to make, more viscous of the fluid, to have a better sweeping efficiency. And as it is the case in the right side. Also, you need to know the rock properties. You need to know the saturations. And by the way, it has been said that if the oil saturation is less than 50%, so it's better to avoid water flooding, because it will not actually work. Another thing is, you should know the drive mechanisms. What's the drive that controls, or what's the source of energy in your reservoir? Is it a strong aquifer? Is it a weak aquifer, or there's no aquifer? Is it like depleted? So you have to be aware of, I mean, is the aquifer acting the same along the structure or not? So all these things, you should be aware of it before starting working on water flooding. Another factors that is important as well to think about, which is like, here we have the cumulative oil recovery due to water flooding, of course, can be determined at any time of the life of the water flooding project, if you know the following factors. As you can see here, first one is oil initial place at the start of water flooding. This is actually the function of floodable pore volume, okay, and the oil saturation as well. Okay, and when I say the floodable pore volume is highly dependent on the selection and the application of net pay, discriminators like permeability and porosity cutoffs. So you should, like a successful flood requires that sufficient oil like be present to form an oil bank, okay, as water moves through the formation. An accurate prediction of water flooding performance, or the interpretation of historical water flood behavior, can only be made, of course, if a reliable estimate of oil in place at the start of water flooding is available. Therefore, there's nothing to rely on, because you don't know what you have, and so you cannot estimate how much can you extract from. So this is a very important thing to know. Another thing is the aerial sweep efficiency. This is the fraction of the reservoir area that the water will contact. Okay, so it depends primarily upon like many factors, like the one of the most factors that it depends on is the relative flow properties of oil and water. Another thing is the production injection patterns. What type of patterns is being used? And another thing, it depends also on the pressure distribution between the injection and the production wells. Okay, and of course, also it depends on the directional permeability, as we have mentioned before. For example, in the water injection project, we prefer to have a good vertical permeability, while in the flooding, we seek for a good horizontal permeability, for better sweeping. Then we have the vertical sweep efficiency. This is the fraction of formation in the vertical plane that water will contact. Okay, and it depends primarily upon the degree of vertical stratifications existing in the reservoir. And then moving forward to the last one, which is displacement sweep efficiency. This actually represents the fraction of oil that water will displace, and I mean, in the portion of the reservoir per volume invited by water. And the important things that the volumetric sweep efficiency is a macroscopic displacement effect, which is a function of mobility ratio. The efficiency of water flooding can be improved by lowering that water oil ratio. So, what is the mobility oil ratio, or what's the mobility ratio? It's very simple. It's the permeability over viscosity, or in other words, it's like a quantitative measurements of fluid, ability to flow through the channel. So at the end of the day, we need to decrease that mobility ratio to increase the sweeping efficiency. Sometimes we can do that by adding, as I told you before, some chemicals um, to increase the sweeping efficiency and make it more viscous as polymer or gel. So then by applying this formula, we can have like the oil niche in place at the start of water flooding multiplied by the three efficiencies we have, then we can end up with the total recovery we can get from that oil initial in place. Okay, here we have the main advantages and disadvantages of water flooding project. Practically speaking, many complex enhanced recovery processes have been, developed through the years of development and experience. But water flooding is currently the most widely used fluid injection process, and it's responsible for a significant portion of oil being produced in the worldwide. For example, in Canada and the USA, the water flood projects account for more than half of the current oil production. I mean, this is a huge percentage, isn't it? And there are, several reasons why water flooding is the most successful and it's widely used. As you can see here, there are some points that makes water flooding is preferred to be used is the general availability of water. I mean, when compared to other fluids, it's more available than any other fluid on this earth, which make it like we can inject it at lower cost compared to other injection fluids. And also, when it comes to water injection, it's much easier to inject than, for example, injecting gas. For gas, we need to have like minimum miscibility pressure. We need to have certain conditions that allow us to introduce that source of energy. However, in the water, in most of the time, we don't need to do that. Even though we might need to test the compatibility between the injected water and the water that is existed in the formations to avoid any formation damage. But generally speaking, is much easier to inject water into the formation than any other fluids. Then we came to the most important things is the high efficiency of water displacing oil, which is like was proved by many years ago, and it has been recorded that if you are lucky, I mean the best conditions that the best recovery that could be gained from the water flooding is about from 15 to let's say 25% of the total recovery. And this is like the best situation, and you should be very happy if your total recovery is about 25 from water flooding. That means you did a good job. An essential key to successful water flood project is like there are two main things: the well planned, which is prior the water flooding, and well run monitoring and surveillance program. So this is like the critical issue. I mean, particularly for the poor quality or the geologically complex reservoirs, that will make it really difficult for you to monitor. And this is the beauty of it. Even with a bit of intentions, water flooding plans and expectations are usually based on a meager amount of data. And the judge's approach is to, to do your best you can under the, all the circumstances, and always be prepared to deal with surprises, Some surprises might be pleasant, okay, and you will be happy, but some of them are not really pleasant. So, but always remember that surprises can provide useful information, and if well interpreted or if interpreted correctly, so you can suggest ways to steer the process towards the optimized water flooding projects. Okay, so let's move on to the disadvantages of water flooding. Do we have disadvantage in water flooding? The answer is yes, we have disadvantages. Yeah, some of them they could have like they could be like surface problems, and some they could be subsurface problems. They could have problem in the case of for example in the subsurface issue we have a certain cases we call it ion exchange. This ion exchange leads to precipitations of unwanted materials. So if we have like salt in the reservoir, such as calcium or magnesium ions, and I inject water with another calcium or magnesium ions, so I could have a problem, and there will be precipitations of these salts, and definitely we will have something called a scale buildup, which causes formation damage, you know, and that will reduce the permeability, reduce the original permeability in the reservoir. So building up the calcium and magnesium or a scale up in general, that might harm the original permeability and reduce it. So this is one of the things that if you are not sure of the compatibility between the injected wells and the water, between injected water and the waters that exist in the formation, you might end up with a scale buildup and formation damage. Another thing, it might not be, in fact, it might not be that issue, but you should always, you know, consider it. The best water that could be injected. I mean, some of you were, might asking themselves like, what's the best water that we inject to avoid this problem? Okay, always there are solutions, but are they applicable or not? And this is the question. Okay, so the best water that could be injected that hopefully like will not harm the reservoir is a low saline water. And when I say like low saline water, I mean less than let's say 10,000 ppm. I mean, the fresh the water, the better for sweeping and the less damaging the reservoir. This is the idea that I've been, you know, learning the whole my life. Another problem is, you know, the corrosion, which is like a big issue, especially when we inject salty water. So again, we came back to the salt water. I'm afraid that you know, the production string includes tubing, casing, wellhead, even the surface facilities. Um, they might be corroded. And actually, I've been experiencing so many times that leaks in the pipes and surface facilities, even though there are corrosion inhibitors are being injected, but it sounds that they are like not enough to prevent that leaking. So corrosion is a very, very critical and serious issue. And of course, if you have H2S dissolved in that water, so this is acidic, so you have acid, salt, and high temperature. What do you expect to have? Of course, that will cause corrosion, and of course, that will damage the equipment and make it very weak in many cases if you didn't pay attention to the waterability and if you didn't pay attention to the corrosion inhibitor for the surface facilities. So generally, these are the main advantages and the disadvantages of the water flooding. Here we have the main stages of water flooding. Okay, so in this slide, we can check when exactly we need to think about water flooding, and also what are the periods that any water flooding project will pass through. At first, we have, you know, the end of primary depletion. When the natural energy is not enough to provide sufficient pressure to keep producing at the desired rate, so that's what we called the end of primary depletion. And obviously, like when water injection equals or exceeds the production measured at reservoir conditions, the average reservoir pressure is maintained, or in some situations, it could be increased as needed, of course. And in those examples, primary depletion stops because the predominant drive mechanism, like whatever you have, like let's say water drive mechanism, uh, are a result of declining the reservoir pressure. So that's why you need to think about introducing a new source of energy. During the time of the constant, when you have a constant or increasing the reservoir pressure due to water injection, the oil recovery is a result of a displacement process, because whenever you have an increment or maintaining the reservoir pressure, that's a result of, displacement of process of water flooding. However, in the areas where the injection is less than the production and where the average reservoir pressure is only partially maintained, in some situations, the reservoir experiences a combination of two things: of a pressure depletion, because the water flooding was not enough in a specific area. And in addition to pressure depletion, we have a fluid displacement. In some areas, there is a fluid displacement. So we have two things. When both recovery process occur simultaneously at the same time, the reservoir behavior is really, really complex and must be analyzed using numerical models. And it's really difficult to analyze it by the conventional methods. So that's why once you are injecting water flooding, you have to be aware as much as possible to keep like the whole area under like the displacement process, and try to avoid any fingering or any channeling, because once there is a channeling or fingering, some areas will be depleted and some areas will be displaced. So we have both of them. So you will end up with a water production and non-pressure stable in the reservoir. We move on to the second period, which is the fill-up period. This period begins when the initial water injection, once we started injection, and lasts until the first response in the production. When we start feeling that the injected water is doing something, when we see the effect of injection water. So when we notice that the first response in the production increment occurred, so this is the end of filling up period. In this period, free gas usually is being displaced. If you have trapped gas is brought into the solutions and the reservoir pressure is restored. Okay, and this period on the average ranges from 5% to 11% of the total total water flooding life. It depends on many things, like the heterogeneity of the reservoir, the fluid pattern, the well spacing, the volume of void space, and of course the saturation of the oil. Okay, so in general, the more heterogeneous and the layered the system, so we have the faster the gas collapse occurs, and we will have short fill-up periods and low peak oil rates during the production incline period, which might be an indicative of channeling or bypassing, or possibly low levels of pressure depletion as well. So these assumptions, of course, they can be confirmed by further examining the gas oil ratio and water oil ratio trends, as we will see at the end of this webinar. We move on to the following period, which is the production incline period. This period occurs when the oil production begins to increase through the peak to the production rate. So the increment of water flooding, this during this period, the production rate steadily increases, but the water cut does not increase significantly. I mean, there shouldn't be an increment of water as much as there is an increment of oil, because logically you are displacing oil, you're not displacing water. Okay, the length of the time required in this period, it's not actually, it depends, as I told you before, it varies, but let's say on average, it's about 20% of the total flood life. Okay, and then we have the plateau period. This period lasts while the oil and water production rates are stable and ends when the oil rate declines while the water rate increases rapidly. So when there is a decline in oil rate and water rate starts to show up, so this is the end of the plateau period. So this period depends largely on the reservoir homogeneity, it depends on the interwell connectivity, and also depends on the oil-water mobility ratio. If the peak oil rate response is weak or sometimes is non-existent, I mean, you cannot even see it because it's really short, that means the reservoir continuity might be at issue. And usually lack of water production and later time combined with poor gas collapse, this, I mean, will confirm this by plotting the gas oil ratio and water oil ratio versus time in some diagnostic plots. Then we have in the last period the production decline period. This period begins after the peak rate has occurred and the production rate begins to decline. Okay, so it continues until the limiting economic rate is reached. In most cases, the production rate decreases as the water cut increases. This is the typical thing. And this period consists of, the large percentage of the total flood life, usually about 70% of the total project life. So after this period, we might need think about the tertiary recovery and try to introduce another fluids in addition to the water. And the same thing, the more heterogeneous, and if you have layered the system, the faster gas collapse occur, and you will have short buildup, and sometimes the plateau period is very short due to water channeling or bypassing. So now we have, let's say, a brief knowledge about what is water flooding and what's the concept of water flooding and what's the things or topics that is related to water flooding I need to focus on more. Here we came to the more practical thing, okay? We will start analyzing the water flooding performance with the field level data. So after reviewing many water flooding case studies before, like a key lesson learned about water flooding monitoring and surveillance is that to use methodological approach, starting from a large scale and proceeding to a smaller scale, from a field to the pattern and then to well level. Okay, this methodological identifies, general opportunities and the problems. Then, it becomes more specific with respect to the scale of individual wells and corresponding problems. So starting at the field level, surveillance provides baseline that can help, differentiate between poor performance and good performance. And then surveillance of individual wells is an excellent way to develop well-specific recommendations, after the reservoir flow patterns are understood. So you have to understand the thing from field level, and then when you go to the well level, you can give your recommendations strongly. Okay. A review of production injection history using plots can be very useful in diagnosing field response. It's usually the starting point of understanding how the field was developed and identify the main production problems. The chart that you see here is the production history of real data, of course, and the production started, as you can see here. Let's talk about the main events about this production. Here we have the red line is the oil rate, and the light blue is the water production, and the dark blue is the injection rate. Okay, and here we have the pressure plot. The the scale starts from 900, so don't get like confused by the scale. Um, the production started in December 2006, and after like 1 year, the oil rate reached about 18,000 barrel per day, with negligible amount of water, with contribution of it was about 16 wells, and the pressure declined immediately after production started. So it was decided, as you can see here, the pressure declined very fast after the production started. So it was decided to inject water to maintain the reservoir pressure. Okay. The injection started in March 2008 with the injection rate about 10,000 barrel per day, and there were like three injectors, and the effect of injection, or the effect of injected water, could be seen after 3 months. You remember the fill up period? It was like very short. You are talking only about 3 months of injection, and the pressure maintained at 1,200 psi. So then we have like more wells were drilled, and the production increased up to 25%, 25,000 barrel per day, and almost no water production. And the injection was about 200, or I'm sorry, 20,000 barrel of water that's being injected per day. The field, witnessed different conflicts and different shut-in periods. For example, in 2011, the field was shut in due to the first conflict in the country and remained closed like for 1 year. And once the production resumed, the injection was not actually started immediately. If you may notice that the space in this period, okay, was not started immediately, um, because try to avoid any water injection. And then we have the longer shut-in periods, which is lasted for like 40 months. Then we have the reservoir pressure. Actually, analyzing the pressure for the field life may not be the good thing. It might be tricky because of the huge variations in the pressure points, like at the same period of time, as you can see here. At the same time, there are some points recorded about like 1,700, and other recorded about 1,100. Okay, of course, in different locations. But what do you think that the source of this big variance in the reservoir pressure? Okay, and this is like a very good questions, and actually we were thinking about this, and now it's time to know like why this the pressure. If you take a deep look, you will find out that the in shut-in period, as you can see here in this narrow, the whole field acted the same. So we come up with the conclusion that statically, I mean, in the static conditions, the field is in communications, and there are no faults preventing any aerial communications. However, the reservoir pressure support is not acting the same along the structure. So by analyzing the material balance, it turned out that, and of course the well testing, it turned out that the aquifer support was not acting the same and causing the variance in reservoir pressure in the producing or in the dynamic situations. Okay, and then, so that's the reason why we have variance in the reservoir pressure. And in shut-in period, the whole field acted the same, and it became narrowing as long as there is, in the shut-in period. Like in this point, there was no point measured, but in this point, they're all the same. And once they opened for production, the variance occurred again. Here we have the voidage replacement ratio calculations for the entire field. Voidage replacement ratio, or VRR, is defined as the total fluid volume injected divided by the total volume of fluids produced. It's very simple. Both, of course, at the reservoir conditions. Ideally, the VRR should be approximately one, equals to one when we have the volume that you inject equals the volume that you produce. And whenever you have high VRR values, that means you are in a situations in which like over injecting. That means you are over injecting. If you are injecting more than one, that means you are over injecting, and the injected water is not going in the right direction. Over injection, could be caused by thief zones taking the injected water, high permeability layers causing, preferential flow, or fractured reservoirs causing direct cycling of water between injectors and producers. All these things makes you have like high or overestimated voidage replacement ratio. And if you have like low VRR values, indicates that in situations in which produced fluids are withdrawn faster. Well, I'm not sure why the presentation moves by itself. Okay. If you have like low VRR values, that means we are in a situation that produced fluids are withdrawn faster than the reservoir per volume is being filled with the injected fluids. And this usually a result of pressure drawdown and increasing free gas saturations forming in the reservoir, which is absolutely undesirable. Um, in the lower chart, of VRR, the optimum voidage replacement ratio that's maintain the optimum reservoir pressure was found to be about 0.6, as you can see here, 0.6. But always remember that this is a field level. And since the aquifer strength is not acting the same, therefore, there should be like more than one VRR representing the different patterns. I mean, this 0.6, it shouldn't represent the whole field because the aquifer strength is not acting the same along the structure. So 0.6 should be subdivided into different areas and different patterns, as we will see in 5 minutes. Here we have the conformance plots. Conformance plot, it's a really excellent plot that indicate how efficiently net water injection affects the reservoir oil recovery. Comparing the net water injection with the resulting oil production, that enhances the understanding of you have influx or you have what we call it an efflux of fluids, as well as the losses of water to non-pay zones. So conformance plots actually are particularly helpful for water flooding due to the low compressibility of like the fluids that is involved in this project, oil and water. So if you plot the oil recovery versus net water injected of movable per volume, you can have different options. Okay. Let's say this is actually the primary use of this plot is to identify the patterns, flow, and losses to non-pay zones. And an ideal case in which the pressure is constant and there is no initial gas saturation and there is no influx or efflux into the area. So the graph should give a straight line. Okay, so if we have a straight line, this is actually an ideal and a theoretical thing. Okay, and it shouldn't happen if you have any like fluid getting into the reservoir, or the injected fluid going out of the like in thief zones like fracture and any sort of channeling. Okay, so this is actually the straight line. But any change in the slope in the conformance plot that may indicate any other conditions. For example, if you have an upward curvature, that means there is another fluid coming into the reservoir in addition to the injected water. And if you have, why? Because the recovery, the same, almost like there's a slight change in the x-axis will have more change in the y-axis, which is a recovery. So that's why there's something helps the oil recovery. I mean, there is an additional source of energy helps the thing that you are injecting. So that's why we call an inflow of the fluid. And then if you have a downward curvature, that means no matter how much you inject, there won't be an increment in the oil recovery. So in that case, that means if you have like a downward curvature, there is a thief zones or there is like a fracture, and this zone takes the water, the injected water, and you will not get use of it. And the problem that you will produce that water without taking any advantage of it. So that's why conformance plot is really, really important, even though it's a field level, but you, of course, it's so important. But in the pattern level, it will be more important because it will take in considerations different aspects. You know, I mean, it will take the location, it will take the strength of the aquifer, as we will see in the next slides. Okay. And if you plot the recovery, this is the real data of recovery factor versus the net water injected as it is calculated here from this equation. Okay, so the recovery factor increases as the net water injection increases until we reach the deviation in the slope. So what we call this point, we call it as a break-over point. So remember this point, it will be really important. The breakover point occurs at the time when there is like a substantial bypassing begins. So if you have substantial bypassing, you will reach the point of breakover point. Normally, for water flooding performing well, the breakover point occurs at approximately about 20% of the total oil recovery for a favorable mobility ratio. But an early breakover points, as it is the case in our example, here it might indicate to heterogeneity or unfavorable mobility ratio. So in general, projects that exhibit early water breakthrough that could be due to an extreme permeability variations and extreme heterogeneity that leads to makes the fill-up period, if you remember, very short and early stages of the early presence of breakover point. Okay, so rapid decreases in the slope of recovery versus hydrocarbon, movable hydrocarbon, that may indicate excessive channeling due to the heterogeneity or fracturing out of the zone and water losses to non-pay zones. Here we have in the pattern level, analysis at the pattern level helps evaluate the regional volume balance and represents the most difficult part of the water flooding management process, because correct analysis requires that you identify injector producer pairs as well as the drive corresponding time, dependent allocation factors. So in the field level, okay, the key performance indicator for a pattern analysis are are two main things: the voidage replacement ratio and the conformance plot. And the same thing here for pattern level analysis. We need to analyze both of them: the voidage replacement ratio and, of course, the conformance plot. As you can see here in this field, it consists of 41 wells, about 25 producers and 16 injectors, arranged in the 8 distinct inverted 5-spot patterns. Okay, so we have 1 per injection well. And the production wells were assigned to each pattern according to their distance, like to the nearest injector. And this is the main idea that was. And were initialized with geometric allocation factors. Like it was the let's say this injector giving about 70% of that well and giving the other 35% to other well. It depends on the horizontal permeability and the directional permeability in addition to the well location. And the production wells were assigned to each pattern according to the the distance nearest to the injector. For water flooding, the most common patterns of injection and production well is a 5-spot configuration, where I have the injector in the middle, and I have like 4 producers in the corners. And this is normally the typical situation. And this is the very typical thing that we do in water flooding. Of course, there are many other patterns, such as like you might have 4-spot, you might have 6 spots or 7 spot. You might have a scattered injectors. You might have like a line to line. You have a one injector and gives to the one producer and so on. And you might have like a peripheral injectors, which like surrounding you have injectors, and these injectors are surrounding the all producers, and these injectors getting closer to the producers as we proceed in production. So this brings us to think about what is the ideal pattern. I mean, what's the ideal pattern scheme for water flooding should have, okay? So if you want to have ideal patterns, you should promote fast roll production response. So this is what really matters. And also you should think in a way that you have keep minimum number of new wells to produce at the desired oil rate and inject at the desired water rate. So this is more economically, if you can say. So try always keep with the minimum rates. And then ensure a maximum volumetric coverage of the reservoir shape and size as well. So this is, as we have been said already, about the volumetric coverage. And then, of course, you can have you should take in considerations the reservoir heterogeneity and anisotropy, if any, existing. And the thing, or the first enemy of water flooding is how to minimize the water production and manage its disposal concentrates. So you have to be careful with the injected producers. Most of the time, it's impossible to meet all these requirements because the field may already have been developed under different considerations, and it has been built during the primary depletion phase, and you were not there. So sometimes it's really difficult to consider all these things. Another thing that it's really I would like you to think, I would like you to focus on, that is well pores may exist with an apparent pattern, but a careful analysis of directional permeability and lateral discontinuity of the reservoir rock, that may cause the actual flow within the reservoir. And sometimes it's quite different with like only if you take considerations the well pore locations. So the well location is not only the thing that you consider. You need to consider the directional permeability and the lateral discontinuity of the reservoir rock. How can you analyze the lateral discontinuity? One of the main powerful tool that I usually do is analyzing RFT, or repeated formation tester. Okay, so it's an open hole wireline instrument, primarily using for measuring vertical pressure distribution in the reservoir. So it can tell us if there is an aerial communications between the wells or not, and also it can tell us the vertical communication as well. And of course, we can have other sessions to analyze the aerial communications. So this is, there are 3 main patterns were decided. one in the north, two in the north, one northwest and northeast, and we have in the south. For this webinar, I will only talk about one pattern, which is in the north. As you can see here, these are the production and injection figures of this specific pattern. The injection started after about a year of beginning of production, and during that year, the production decreased to 1,200 psi. And of course, it will decrease more if we didn't start injection. So that's why we needed to start injection, or we need to start water flooding, let's say. And have you noticed that the pressure points were smooth, and because they have like the same pressure support in this pattern? So that's why, I mean, this pattern were collected somehow wisely, because we can see a smooth pressure and there's good communication, and they are experiencing the same pressure support. Okay, so that's the thing. Okay, and then we can have the target reservoir pressure in that pattern, or in that field. It was decided to be at 1,200 psi, and the corresponding VRR to maintain that pressure was 0.5. So the VRR was chosen to be the optimum VRR, which is 0.5. What does it mean when I say that the VRR equals zero point 0.5? This is a question. I've already said the answer. It simply means that the water flooding gives us 50% of the support to maintain the pressure, and the other 50% comes from other source of energy. In the case of, in our case, it was a water influx. So we have a water influx, but this water influx is not enough to maintain our reservoir pressure. That's why we needed to inject water. But how much water we need to inject, it depends on the optimum reservoir pressure that we have. And what's the optimum reservoir pressure? Optimum reservoir pressure, theoretically, it should be like above bubble point by 200 and less than the fracture pressure by 200. And of course, it should be it should like be able to support the desired oil rate. Okay, so this is the optimum reservoir pressure. According to that, we have the optimum voidage replacement ratio. But here we have, is the VRR of 0.5, is it optimum for the whole field life, or it might change? I believe that this is the historical optimum VRR, and maybe in the future the situation is different, and the desired rate, it will be different. So therefore, the VRR, it should be different. I will not say less than 0.5, but I would say it must be different. Okay, here we have the conformance plot. You remember the conformance plot, the same idea, we will apply it for the specific pattern. As you can see, at first we have a straight line, then we have an upward curvature, which indicates that there is an influx in addition to water flooding, which proves the idea that, has previously said in the last slide, which says that there is water influx in addition to the water flooding. Okay, I'm not sure how much time I've been talking, but the presentation time will be like only 3 slides, and I will finish this presentation. Don't worry, they are very short slides, but they're very interesting. The water flooding analysis is that at the well level is really essential to assess the health of individual producers and injectors. So this is okay. You understood the field level and the pattern level, but now it's time to make recommendations. And you will not make recommendations on a group of wells. You have to analyze each well separately. Okay, so let us start with the first method of the well level analysis, is the heterogeneity index. Okay. For the heterogeneity index is a process that quantifies the well behavior dispersion, comparing individual wells to the average of the well group according to the formula that you have here. So let's say a value of well, let's say A1, whatever this value, it's the oil rate, if it's the water cut, the gas oil ratio, the water cut, the water rate, whatever, and then compare to the value of the group of the average. I mean, the average of the group. I'm sorry, and then we subscribed it by one to have like an index, okay, to be normalized to zero to calculate the conditions. So we will end up by three scenarios. Scenario number one, the well performance matching the average of the group, and then you will have the heterogeneity index of zero. That means your well is equals to the average, and there's nothing to worry about. And the second thing, if the well is performing above the average, we will have a heterogeneity index greater than zero, and the wells performing below the average will have HI, or heterogeneity index value, is less than zero. We usually do, like as you can see here, a scattered plot of X and Y coordinates that can be used to identify the location of the problem wells, okay, in the field. And from that plot, you can recognize your wells. So you know the location of the wells that performing good, like which they represent at high oil and low water, as you can see here in this area. You have the wells that have high oil and low water, okay. So and also the wells that are producing underperformance, which they have high water and low oil, which they represent here in low oil and high water, and this is in between. And then you can have them, you can have their locations, and sometimes you do like a correlation between the wells that have problems, and they might be located into next to each other, or they located into a distinct geological feature. So this is actually is really helpful to know where to focus. And after that, after like identifying the wells that have problems, it's time to know the reason behind these problems. I mean, this is what we are doing now, like in a minute, by practicing some diagnostic plots. So now you located the wells that have problems. Let's say it has high oil and low water, and this is let's say they are located somewhere here. Okay, now it's time to know why this problem. We can do that. The first thing we think about is a Cham plot. In 1995, well, when I was in the age of like 3 years, Mr. Chan proposed a technique to determine excessive water production mechanisms. So, and that was the beauty of it, that was based on the results of, simulation studies. And it was observed that the shape of water oil ratio versus time, which is the plot that you have here, differentiates between the water production due to coning or channeling. The water that comes from top perforation due to coning, or from upper perforations due to channeling. This Chan graph, there are 3 periods that can be identified on this plot. Okay, so let's divide them very quickly. The first period is the prior to the water breakthrough, when there is no water production or dry oil is produced. There is a constant ratio in the case of the two-phase of production. So you have a constant oil, a constant line, there is no water production. You haven't have any water production. And then once you have a breakthrough, after you have a breakthrough, we have 2 main periods. You have earlier period, and you have later period after breakthrough. So let's start with the earlier period after breakthrough. For coning, the water oil ratio increases somehow slowly and gradually, approaches at a constant value at first. And then, however, for channeling, the situation is a bit different because the water oil ratio increases rapidly with water breakthrough in a higher horizontal permeability layer. So in channeling, it increases at the constant rate until the next higher horizontal permeability layer breakthrough. And because of that, we will have like a stepwise behavior is usually being observed. And this is the main differences between coning and channeling in the early period. So in the early period, for coning, it increases slowly, and channeling increases rapidly. But in the later period after breakthrough, the situation is somehow the opposite. For coning, water oil ratio increases rapidly as the water cone becomes highly conductive channel. It finds its way to the wellbore, so it will increase rapidly. However, for channeling, water oil ratio increases with a constant slope because it was like a steady, and there's nothing will make it increase until it find another better horizontal permeability. you know so this is actually the main differences between water coning and water channeling. Another thing, which was like very very helpful, and you can depend on that, the distinction between between channeling and coning. If we take the derivative of water oil ratio versus time, you know for coning, the change negative slope is observed usually. As you can see here, we have a negative slope of water oil ratio, the derivative of water oil ratio. And for channeling, it's the opposite. We have constant positive slope is usually observed. So this is the main difference between water coning and water channeling. Okay, if you have water coning, what do you think? I mean, the proper solution is usually to isolating the lower perforations. If you have good, if you don't have like good vertical permeabilities, and just take in considerations the distance to free water level. Um, and if you have channeling, the situation is a bit complicated, and you might need to choke back. You might need to choke back the producer or reduce the injection rate. That all these things are applicable for controlling that water. But anyway, this is a diagnostic plot. And here we have an example of the real data. First, we have a straight line before water breakthrough, then the water air ratio increased and took somehow stepwise shape, which is an indication of water channeling. And of course, you cannot judge the channeling or coning based only on Chang graph. This is, at the end of the day, it's only diagnostic plot. But this there must be other techniques to prove the idea, like PLT and many other things, tools that could identify the source of water. We came finally to the last but not the least part of the presentation or slide, is the whole diagnostic plot. Maintaining the injectivity index of a well at the designed value is important to the success of water flooding project. And a whole plot is a simple method of analyzing the injectivity data to assess the reasons for any change, and of course to take any actions that can solve any problems. Um, in 1963, Mr. Hall, presented a technique to analyze the skin effects of injection wells, and the techniques usually use takes into account Darcy's law for a single phase, and its assumptions like steady state Newtonian flow on a well that is centered in a circular reservoir, and assuming that the permeability is constant, the thickness, the viscosity, all these things are constants. And he had this plot, this lovely plot, and the plot of weighted sum of the summation of the surface injection pressure times versus the cumulative water injection. So we have here the cumulative water injection, and you have the wellhead pressure versus time. And then you will have like mainly four patterns. The first pattern is when you have at first a straight line, and then this straight line somehow have an upward curvature. So no matter how much you increase the wellhead pressure, the injectivity, the cumulative water injection does not increase. I mean, the formation does not accept the injected water. So this is an expected to be like damaged wells, and it might need to be stimulated by doing any means of stimulation like fracture or acidizing to improve the permeability of that formation, and the well will be able to take more, fluid. And another number two, as you can see, the dashed line, the green one, you have a straight line at first, and then we have a slight upward, um, a slight curvature upward, and this is it could be due to gradual plugging the well. So in this situation, we might not need to do like stimulation or acid as much. We might only need to do acid wash to clean up the well bore, and we might have like a better injectivity index if we did like only a partial or acid wash cleaning. And if you have a straight line, that means there is no change, there is no plugging, there is no damage. Once you increase the wellhead pressure, the well will take more water. So this is the typical thing. And another, or the last one, if you have a straight line, then the curvature goes down, or the curve goes down. So in this situation, that the well is stimulated, either stimulated by doing fracture. Sometimes you inject above the fracture pressure, so that's why it creates a bath, and at the same wellhead pressure. So there is a huge amount of water is being injected at the same wellhead pressure, or it might found like a sudden channeling that becomes a conductive path to the fluid to enter to. So this chart can tells you the health of the stat or the status of your injector, and of course it does matter to you the health of injector, because this is the one who's responsible for delivering the water to the oil in the reservoir. Thank you so much for your attendance, and this is all what I can tell about water flooding, and I appreciate your